Okay, Assalamualaikum and welcome to another supplementary lecture. Okay, uh, welcome to EPO 640 on electric drive. So, this will be our discussion on AC drive. So, this will be the last lecture on this topic, AC drive. So this will be further discussion on the vector control, okay, on PWM and vector control. Okay, so this is a supplementary on the last lecture slide that we had. Okay, before this. So for vector control, okay, so if we look at voltage to frequency drive, okay, it's from you have sensor or sensorless. Okay, so that is if you have a scalar control or a vector control. Okay, so if it's a scalar control, you have your V2F, okay, voltage to hertz control, and they have, okay, so we have discussed this on our previous lecture. And for sensor, you have your vector control. Okay, so vector control also is divided into two. That is the direct torque control or the field oriented control. So from last lecture we discussed on the FOC, okay, and this will be very advanced. Okay, this you have DSC, SVC, okay, direct FOC. So this usually is on the advanced drive, okay, power electronic drive. So this will not be in your examinations, okay, and your final test. Okay, so we look back on the equivalent circuit of a practical motor. So you have two examples here. Okay, you have this example here. So so for this example is for a one phase of a three-phase induction motor. Okay, so you can look at your textbooks, okay, on your any reference books. So usually they have this similar explanation on the equivalent circuit, okay, for practical motor. So for example, this will be a equivalent circuit for a 5 horsepower 2-pole 460 volt 3-phase 60 hertz induction motor, okay, at full load. So this will be an example. So you have your MMF in your flux in 97%, okay, and on synchronous speed, okay, 3600 RPM, okay, and this will be the rotor speed, okay, and the torque. Okay, so you have all the information on the induction motor. Okay, and here's another example. Okay, so okay, so the same equivalent circuit, and we can see the at full load the flux, okay, in the air gap is slightly oriented, so but the orientation is just 2.4 degrees, okay, with the respect of the rotor current. Okay, so you can see on the rotor side and on the stator side. Okay, so slightly what you call it, the angle is slightly disoriented, only 2.4 degrees, and you can see that the rotor speed and the synchronous speed is quite near. So you have very low slip. Okay, so this is during the MMF, the magnetic flux is at 97%. Okay, this is created during voltage is 265 volt and 60 hertz. This is just an example here, example of this 5 horsepower motor. And we can see that if we change a little bit on the parameter, so this is during a lock rotor condition. You can see that you have your rotor speed is 0, and during this you have your synchronous speed is normal. So this is during lock condition. And you have your flux is at 42%. Okay, and you see a huge distortion up to 59 degrees. Okay, so at the lock rotor condition, the flux in the air gap is oriented at 59 degrees with respect to the rotor current. Okay, so one of the examples. And last one. Okay, the third example will be during flux is at this was the previous example. This was the previous example was on 97 degrees flux. So and in this case, this is at 76% flux. Okay, and you have this is during low frequency. Okay, 6 hertz. Okay, low frequency, low voltage. Okay, 26.5 volt, 6 hertz. Okay, and you have your synchronous speed. Okay, and your rotor speed is 270 rpm. Okay, this is during low speed. Okay, and you can see the flux, the disorientation is only 2.4 degrees. Okay, so you can see that you have problems arise during low speed. Okay, and in this case, the torque. Okay, so you have a big drop in the torque at lower speed. Okay, and so those are three examples. Okay, that we can see for a volt to hertz on a practical motor. And next we will be looking into operating mode for a three-phase converter. Okay, so mainly they will be execute this using PWM method. Okay, PWM method. So already we have discussed this PWM. You have discussed this. You have been doing PWM back in the subject of power electronics. Okay, and also we have discussed a little bit of PWM on our previous lecture before this. Okay, so let's see. So you know PWM, you have your carrier and your modulation index. Okay, modulation wave and your carrier wave. And so this figure shows us a simple method to generate the PWM pulse train. So by comparing your carrier with your modulation, so you will produce this below here, your PWM signal. So the signal, okay, in the red sine wave is compared with the sawtooth waveform blue. Okay, and when the latter is less than the former, the PWM signal, okay, so down here is in high state, and when the latter is in the opposite, okay, so it's on the low state. Okay, so when okay, the red line meets the blue line, so it will switch on and off and on and off. So it will create a pattern that you can see on the graph below. Okay, so this figure shows so this one it's the principle of a delta PWM. Okay, So you have the output signal in blue. Okay, output signal in blue is compared with the limits. Okay, limits in the green. Green is the limit. Okay, and this limit corresponds to the reference signal on the red. Okay, on this sinusoidal reference. So the offset is given by the value. So every time the output signal reaches one of the limits, the PWM signal changes the state. Okay, same method. Okay, so for this, so we will look at on some examples. Okay, operating on the three-phase converter. So in this example, you have this criteria. You have your fundamental 100 hertz, okay, 446 volt RMS, and it's running at 3000 RPM. Okay, and the carrier will be 100 hertz, 700 voltage peak. Okay, carrier. So for this example, speeds above the base speed. Okay, in this case, the base speed is 1800 RPM, but in this example, it's running at 3000 RPM. Okay, so implying frequencies above 60 hertz, the converter operates in a rectangular wave mode. Okay, and the step voltage is applied during 120 degrees interval, and the effective line-to-line voltage is held constant at 546 volt. Okay, so it's so this figure shows the typical EAB, that is the electromotive force voltage waveform. Okay, when the frequency is 100 hertz. Okay, and note that the peak amplitude of the fundamental voltage is slightly greater than 700 volt. Okay, DC voltage. So yeah, so the peak will be slightly higher than 700 volt, but 546 is the RMS value. Okay, so another condition. Okay, another example. Okay, when you change the parameter. Okay, so in this case, it's 1410 RPM. Okay, and the frequency is fundamental frequency is 47 hertz. Okay, voltage is slightly lower. Okay, so it's a V2F condition. So you reduce the frequency, also the voltage will reduce. Okay, and the carrier also is but the carrier voltage will not change. Okay, but the frequency will change a little bit. So for this condition, okay, this is for a 47 hertz. Okay, corresponding to a synchronous speed of 1410 RPM. Okay, so the carrier frequency is 235 hertz and synchronized, to be exact, 5 times the fundamental frequency. Okay, so the phase angle of the carrier is also synchronized with respect to the fundamentals in order to produce a symmetric pulse. Okay, and the peak value of the fundamental voltage is 605 volt. Okay, which is less than 700 volt. Okay, peak voltage. Okay, next we reduce further. Okay, we reduce further the frequency and the voltage. Okay, and so this time is exactly 7 times. Okay, that is 35 hertz. Okay, and note in the passing that if the voltage, the volt seconds under the dotted sine wave during 1/2 cycle is are equal to the voltage second of the corresponding 700 volt pulses. Okay, so this generally rules hold for through all the wave shapes illustrated here. Okay, So okay, and next we will look further extreme. Okay, we will look on the last example. So this will further reduce the speed. Okay, you see 11 hertz. Okay, and or 101 volt. Okay, so in this case it is typical of the wave shape obtained when the converter is operating in the unsynchronized mode. Okay, so in this mode the carrier frequency is fixed at 300 hertz. The individual pulse duration is very short. Okay, but nevertheless, although the figure cannot show it, their width varies in the course of each half cycle. And in the middle of the cycle, where the peak voltage is 142. Okay. So the pulse width is only 0.68 millisecond, and the calculation is made. Yeah. Okay. So we can look at the okay. So this will be the example of this is a example of a operating mode of a three-phase converter for a this is for electric train. Okay, electric train. So you have items 1 to 10. Okay, so you have okay, so this will be on top of the train. You have your number 9 will be the trolley line where okay, if you look at your KTM commuter, KTM commuter, the overhead line. So this will be number 9, okay, where the electricity is supplied to the train, and it will be it will be connected to the pantograph. Okay, so the pantograph is like a cable or a stick that will capture the electricity from the trolley line. Okay, and it will supply the electricity to the motor. Okay, so it goes to the transformer, okay, to the system, to the PWM converter. Okay, and maybe this is the AC line. Okay, AC going through here. So maybe here AC to DC. Okay, probably AC to DC. Okay, converts from AC to DC, and it goes through the filter, the all this okay, what you call it, the power condenser. Okay, all the capacitors, and to the PWM converter here, another okay converter here, which converts okay the required frequency or required okay, with all the parameters that is inputted into the PWM converter in order to drive the motor. Okay, so along the way you have your switches, okay, all these components here that helps the transfer of electricity energy to the motor. Okay, so that will be the example of a operating mode of a three-phase converter. And next we will look into flux vector control, which we already discussed previously. So just from a different textbook, they have a more slightly different way on how to explain vector control. So whichever textbook that is easy for you to understand, so you should go through the reference or textbook that you think that is more easy to understand. Okay, so in this case okay, so this is from the textbook, Prof. Rashid's textbook. Okay, so Power Electronics by Prof. Rashid. So I think this is a good explanation from Prof. Rashid. So you have since you cannot, you cannot directly control your rotor. You cannot supply voltage and current to your rotor on a AC machine. Okay, so what you need to do, what you can do for an AC machine is you can only supply voltage and current, okay, through the stator part, stator part of the machine. So so as in DC machine, these two currents are roughly 90 degrees to one another, and their vectors some makes up the stator current, which can be measured. Okay, and this is what makes the vector control of the AC motor more difficult than its DC counterpart. Because we cannot control the rotor part of the machine. Okay, so the challenge for the AC flux vector drive is to distinguish and control these two current vectors without the benefit of two separate circuits, and only being able to measure and control the stator current. Okay, so flux vector control, we want to control the motor like a DC motor, but since we cannot connect the rotor part of the AC motor, so we need to only access the stator part of the motor. Okay, so how they do it? So the strategy of the AC vector control is to calculate the individual current vector to eventually enable separate control of the flux current and or the torque current under all speed and load condition. So so as in the DC drive, the aim is to maintain a constant flux current to the motor. So the calculation of the current vector involves the measurement of the available variables, okay, such as the stator current, the stator voltage, the phase relationship, the frequency, shaft speed, and applying them to the motor model, which includes the motor constants. Okay, so all the stator resistance, the inductance, okay, rotor resistance, all that. And because of the many variables, there are many possible applications of a motor model. Okay, so from simple estimation to a complicated, more comprehensive and more accurate detail, okay, to the motor model. So of course all this requires more processing processing power is required, so you will need microcontrollers, microprocessors in order to execute this. Okay, compared to a normal DC motor where it's straightforward. You can control your rotor, okay, by limiting the voltage using resistors and so on, manual. But for this, it will be more complicated, and it will use more processing, more calculation power. Okay. But it's not a problem now because you have advancement in these microprocessors, microcontrollers, and production wise and cost wise is very cheap, so it will not be a problem now. Okay, and you can see here from the stator part of the motor, you can measure the voltage, okay, the voltage and the current input to it. Okay, and the rotor part, that is the IR, and maybe the current, EMF, MMF, you cannot measure that. Okay, it's hard to measure. Okay, so with that, we only can control the voltage and the current of the stator part. So another good figure that is shown here. Okay, so you have your current source, current or voltage source. So in this case, your current source, So of course, what you supply, the current will affect the rotor. Okay, so on the rotor part, you can estimate. You can estimate, or it cannot be measured. You can estimate on how much, okay, current passes through each phase of your rotor. Okay, rotor. And so for this example, you have, for example, if you have your phase A is 32 amp, phase B is 18 amp negative, and phase C is 14 amp negative. And on the rotor side, your X, Y, Z phase. Okay, so for X, after induced, the current is 30 amp. Okay, positive. Y, okay, Y, so from 20 amp, it will induce back to 80 amp at the stator side. Okay, and so on. So this is example. And you have your instantaneous current in rotor and stator windings. Okay, so in this case, it's a 2-pole 3-phase inductor motor. And here we can look at the instantaneous position, okay, of that. And this comes to the calculation of the vector. Okay, so the current in the 3-stator coil produces a magnetomotive force that are oriented at the right angles to the plane of the individual coils. Okay, so yeah, so that's by applying a right hand rule. Okay, for phase A, so for example, for phase A, produces an MMF of 32 amp. Okay, and times the number of turns in the coil. Okay, in the motor, in the stator. Okay, in the stator, so it sums to through 320 amp, and the directed vertically up. Okay, vertically upwards. And from B, okay, so phase B produces 180, okay, directed slightly at left, okay, and 60 degrees left from A, and also C 140, 60 degrees to right. Okay, so the vector sum of A, B, and C is the IS. So this will be the stator current. Magnitude is 481, and the direction is slightly 4 degrees to the left. Okay, so for this moment, for this second, for this moment, when we measured the stator, okay, stator of the motor, so for phase A, phase B, and phase C, for this moment, okay, the vector and the magnitude of the current, okay, the motor current is this value. Okay, so this is what we call the instantaneous magnitude and orientation. Okay, so this will happen for each second. Okay, and you can see that based on the the input voltage. Okay, input voltage for phase A, B, and C is sinusoidal. Okay, and you can see that IS will rotate. Okay, will rotate based on the value of A, B, and C. Okay, and also happening in the rotor part of the motor. Okay, so that previously it was on the stator part, so this is on the rotor part. Also, the same thing happens in the rotor part. Okay, so you have your the induced current on the rotor part on the X, Y, and Z. So you have 300 amp, okay, for X, okay, 200 amp, 60 degrees from X, X-axis, okay. 60 degrees from left to X-axis is 100 amp for the value of Z. Okay, So this is also happening in the rotor part. So this is the instantaneous magnitude and orientation, okay, of the rotor MMF. So this is also spinning. If you take all the seconds, okay. So this is instantaneous. Next, it will go slightly left, okay, and it will keep rotating, okay. And so the total IS and IR, okay. So you have this combination, the sum of the stator and rotor MMF. So we can see, now we can calculate the IM. Okay, so this is what we call the rotating magnetic field. Okay, rotating magnetic field. So we calculate the IS we can measure and we can calculate. IR is also we can measure based on IS, and in the result we can find the IM. So IM is the rotating magnetic field, okay, or we call the slip, not the slip, the rotating magnetic field. So this will be referred to the speed of your motor. Okay, so IM cannot be directly measured, so it needs to be calculated, okay, using the flux vector control. Okay, so yeah, we cannot calculate manually at 1 second. So it needs to have a computation power in order to execute this. Okay, and yeah, you have this computation power. You will need all this inverse transformation, okay, transformation from DE, DQ, DS, QS to the three phase A, B, C. Okay, and this can be further read. Okay, you can, if you're interested in this topic, you can further read it in the power electronics, okay, textbook from Prof Muhammad H. Rashid. Okay, but in his book also is just on the surface. So you need to read on a specific book on this flux vector control in order to understand more on this. And this is quite complicated. Okay, quite complicated. It's more on the control. Okay. And actually from the previous lecture I have posted a video on this vector control, so you can try to look back at the figures that I've shown, okay, that I've inserted within the previous lecture. So it will hopefully you can understand what's the function of this vector controller. And this will be, okay, so this will be example of a practical variable speed, okay, block diagram of a flux vector control. Okay, so you have your of course you have your the microprocessors will capture all the current feedback, the speed feedback, okay, and will dictate okay, based on the speed reference, okay, speed regulator, okay, all the flux regulator to and sends the signal to the PWM switching logic in order to operate the power electronic controller, the converter, that will feed the voltage, the current to the induction machine. Okay, and also again, if you are interested in this topic, you can read further, okay, on this in the practical variable speed and drive and power electronics, okay, by Malcolm Barnes. Okay, okay, and hopefully this will okay, you can hopefully this will you are better understand on the topic of vector control. Okay, okay, so for now, thank you and have a nice day.